Let f be a polynomial with real coefficients, and then this integral pq, where we're integrating between p and q, p is less than q, is defined as this. Got the function, which we're then squaring, and we're minusing the function which with the modulus of x as an argument, which we're then squaring. So both of these are going to be positive. Now let's just remind ourselves what f of the modulus of x looks like. So if I had a function that looked, I don't know, like that, that's my I'll just say f of x. Now, f of the modulus of x, if x is positive, it will look exactly the same. Because remember, the modulus function, if x is positive, does nothing. But if it's negative, then f of, say, minus 2 would be f of 2. And we're going to end up getting a reflection of the green part in the y-axis. It's going to end up looking like this. We're then, of course, squaring both, which I'm not going to do on the graph, and then we're subtracting them. And we're interested in these three different statements. So the only ifs mean implies left to right. Now, first up, it's saying that the integral is going to be 0. Well, the integral being 0, sorry, implies that p is greater than 0. And you can see that, for example, if p was here and q is here, we would get 0. It's just, can we get any other p, for example, such that we would get an integral of 0? And the answer is actually yes. Because what if, actually, when we took the modulus of x and we found the function of it, it was the same? I.e., what if we had an even function, something like this? Because in that scenario, when we reflect it, when it's even, I mean it's symmetrical already about the y-axis, it's going to look like this. If we then square both, okay, it's going to get bigger or whatever. But now, if I find the integral between p and q here, for example, then both of them are going to be exactly the same, and I would get 0, which means the integral being 0 does not guarantee that p is greater than 0. It depends on the function. So this one is not necessarily true. Let's look at statement 2. So a negative derivative, i.e. the function is always going to be decreasing, implies that this integral is going to be less than 0 for all p and q less than 0. So let's just consider this kind of situation. Some sort of decreasing. I mean, it could be a straight line or it could sort of be something else. Right, so that would be my original function. And then if I find f of the modulus of x, I would reflect here. Then if I square it, I'm going to end up, okay, those two would sort of end up in the same place. Kind of depends. If I make this like nice and flat, then okay, it would look, okay, maybe it would look like that. And then if I square it, the blue one is still going to be above the red one everywhere. So if I do the integral, it's going to be, say, this blue area. Obviously, I have to square it, so it won't quite be that blue area, minus the red area. But whatever the equivalent is, the blue area is going to be bigger. And so I'm not necessarily going to get anything less than 0. And therefore, this one is also, it's not necessarily true. The gradient is negative. Okay, I could draw it. I changed it, didn't I? I drew it like this, so it stayed the same there. And then we're looking for p and q being less than 0. So I found this, I got to square it, but I found this blue one, I found the red one, which when I square it is going to be below, and I am going to get a positive answer. So yeah, this one is not guaranteed. This takes us to the last statement, that the integral is greater than 0. This implies that p must be less than 0. Well, however I draw my function on the right, let's say if p is more than 0 and q is here, when I do f of the modulus, it's going to be exactly the same. So actually, when I do this integral, I will always get 0. And therefore, the only way I could get 0, sorry, something greater than 0, is when I move it over here. And then we can have a setup a little bit like I did here, to be honest. So actually, this one is true, which means our answer is going to be D. Well done on this question, on all the challenges in this paper. It can be pretty tough in places, but every time you do one of these challenges, you learn something, hopefully, and it's lots to take away. Even if you don't master the papers, it will come together with time. Keep it up. Thanks.